Hello, welcome to today's session on Poisson distribution. Now we'll discuss what are the scenarios or examples where we have to look towards the Poisson distribution. One scenario is, suppose if we consider the number of cars passing through a toll plaza on a national highway, and we want to model the arrival of cars where we have to go for some kind of probability distribution. If you kind this scenario, is it possible for us to apply the binomial distribution, which is already familiar? So, where if we want to apply binomial distribution to model the scenario, we need to know the number of cars arriving, that is, we need to know the value of n. But in this case, we are not aware of the number of cars coming in, therefore, we can't apply binomial distribution. Then what is the alternate or what is the distribution which we can use to model the given scenario? So, for in such cases, the Poisson distribution is the one which is very useful as well as helpful. And what is this Poisson distribution, or when we need to go for this Poisson distribution and how to use the Poisson distribution, we will see in detail. Suppose in binomial distribution, if we see where n is very large, that is one scenario, or there is no clue about the value of n, that is there is no upper bound for the value of n, and if the probability, like what we have been discussing in with respect to binomial distribution, that probability p is a small quantity. In such cases, what we observe is this, if we consider the mean of the binomial distribution, that is n into p as discussed in the binomial distribution, this mean of binomial distribution, which is np, almost behaves like a constant lambda. So, taking this clue, then we are continuing this and we are using this scenario and we are going to use Poisson distribution to model this situation. So, what is this Poisson distribution? Here, if x is a discrete random variable whose probability distribution function, what we have been discussing, is given by p of x equal to e power minus lambda, lambda power x by x factorial, where x takes values from 0, 1, 2 and so on up to infinity, where here the parameter what we have used or mentioned is lambda, which is the parameter of the distribution, and where we need to find this lambda, and by using the lambda we can model or we can use the Poisson distribution. So, here and one more thing we can observe is, if you see the values that random variable x takes, that is x takes values from 0, 1, 2 so on up to infinity, that is we can take values from 0 to infinity. And here one more observation or one more point to remember is the parameter of the Poisson distribution lambda, which is always greater than 0. So, now whenever we discuss, like whenever we define or discuss distribution or random variable, we discuss or we talk about mean of the distribution as well as variance of the distribution. Now, the same discussion we can continue with respect to Poisson distribution. Now, how to find the mean of the distribution, that is mu equal to expectation of x, as we have been discussing. So, which is nothing but summation x into the corresponding probabilities, that is probability distribution. Right. Now, if we use this p of x here, e power minus lambda, lambda power x by x factorial, and simplify, then we will arrive at lambda. Similarly, coming to variance, so we know that lambda square is the variance, which is nothing but expectation of x minus mu whole square, and this is nothing but which can be written as expectation of x square minus expectation of x whole square. So, now this expectation of x is already familiar, that is the mean of the distribution, which is lambda, and we can calculate the expectation of x square. How to calculate is, this is nothing but x square into p of x, where p of x for this distribution as discussed is e power minus lambda, lambda power x by x factorial, where x takes values from 0 to n. Now, if we simplify the expectation of x square and if we plug in the value of e power x, which is already known, that is lambda, then we will get the variance of the distribution, which is lambda. And if we observe this Poisson distribution, here expectation of x, that is mean of the distribution, is lambda, as well as variance of the distribution is also lambda. That means we can arrive at a conclusion saying that for Poisson distribution always mean equal to variance. Not only mean equal to variance, this mean and variance both are equal to the parameter which we had in the distribution, that is lambda. If we recall the relation between mean and variance in case of binomial distribution, that is mean is always greater than variance. That means we can say if x is a random variable which is discrete and the relation between mean and variance is such that mean is greater than variance, then we say the random variable follows binomial distribution. If mean equal to variance, then we say it follows Poisson distribution. Now we will take this example where in a given city 5% of the drivers get at least one parking ticket per year, and here out of 400 drivers given, so we need to find what is the probability that 5 will get at least one parking ticket, and the second one is at least 4 will get at least one parking ticket in a year. So here we are going to use Poisson distribution, where here the 5% is given, that is the probability P is given, and here the total number of drivers, that is 400, is given. And if we want to use Poisson distribution, then if you recall, the Poisson distribution is given by e power minus lambda, lambda power x by x factorial. So to solve this, we require the parameter value lambda. How to find lambda value from the given data? So in this case, what we have to do is, as lambda is not given directly, we have to use the binomial approximation to Poisson distribution, that is lambda equal to NP as discussed. So by using this, we can find the parameter value, then we can look into the problem. Now here lambda equal to NP, where lambda equal to 400 and probability is the 5%, that means lambda equal to 20 here. Then coming to the first problem, what we need to find is what is the probability that 5 will get at least one parking ticket in. That means here we have to find what is the probability that the random variable takes exactly 5, that is P of x equal to 5. So this is what we have to find. As it is following, or it follows Poisson distribution, we have to use e power minus lambda, lambda power x by x factorial. That means here e power minus lambda, that is 20, and lambda is 20, power x, that is 5 by x factorial, that is 5 factorial. So this is the probability that we are going to have. Next, coming to the second one, so at least 4 will get. That means here we need to find, if we take this one, we need to find the probability that this random variable takes at least 4, that is P of x greater than or equal to 4. So if P of x greater than or equal to 4, this we can write as 1 minus P of x less than 4. We know, because if I take this as P of a, then we can write it as 1 minus P of a bar, where P of a plus P of a bar equal to 1. That concept if we use, P of x greater than or equal to 4 is nothing but 1 minus P of x less than 4. Now it is nothing but 1 minus P of 0 plus P of 1 plus P of 2 plus P of 3 plus P of 4. Right. So where we have to use this P of x and for every value of x, and we have to find, then it is going to be 0.735. And if we simplify this, I will get 0.17 in this case. So like this, in a given situation, how to use or how to find the Poisson distribution is, so one is, if it is clearly mentioned, it is the value of lambda, then we use lambda value, then we will find the probabilities what we require. If not, then we have to use the binomial approximation to the Poisson distribution to find lambda value, where by using lambda equal to NP. Then once the parameter of the Poisson distribution is available, then we can find the probabilities we require. So, like this the Poisson distribution can be applied. And to recap, so when we need to apply Poisson distribution, that is when n is very large and p is very small, that is the number of trials is very large and the probability of success is very small, that means where NP becomes almost like a constant, then we have to apply or we have to look towards the Poisson distribution. That means if it is an event which is the rarest of the rare events, then we have to model it by using Poisson distribution. Once it is a Poisson distribution, then it's the probability distribution function is e power minus lambda lambda power x by x factorial, where x takes values from 0 to infinity. And one more point that we need to remember is, for Poisson distribution always mean equal to variance, which is nothing but the value of the parameter. So with this we conclude the topic Poisson distribution.